could bubble in 85 to the top survey, thank you. Hey, if you could bubble in 85, this would be helpful. And just survey.
Oh, sorry.
Oh yeah, thank you. All right, hey everybody, I'm John, and I'll be the instructor today for Calc 2, helping out. I'm going to pose questions at the end. If you guys have any questions of what I'm doing throughout, feel free to ask questions. But with any additional time that I have then, be it that I end early, you guys can come up, ask questions. I can put it on the board, or if you have like specific questions, you can come here and I can look at it. All right, today I'm primarily focusing on integration and series. So let's start off with some integration. Hey, how you doing? Here's a survey. If you can bubble in 85, that'd be helpful.
All right, thank you.
Oh, okay. Maybe just focus. Okay, that's a little better. All right, does anybody know what we would do first here? Any thoughts? You can just shout it out, like what you think might be able to do. On these surveys I'm passing out, you want to bubble 85. All right, perfect. Yeah. So when assigning parts, we usually would use parts for when you cannot integrate at all for one of the functions, or when there's two different types of functions. Here we have the case where it's two different types of functions. We have a trig function with just a regular linear function. And then when we're assigning u and v, we want to look if we can integrate both terms. If you can integrate both terms, then you start to look at u. Whatever makes a simpler u, that's what you assign as your u. So in this case scenario, we can integrate both. So we're going to assign u as t, making du dt. Assigning v, dv, as secant squared 2t dt. Integrating both, taking the integral, get 1/2 tangent 2t. Can anybody see that? All right, nice. Using our parts formula, we have u dv of uv minus the integral of v du. Substituting in, we're going to get t times 1/2 tangent 2t minus the integral tan 2t dt, and we're pulling out that 1/2. Simplifying, we get t over 2 tangent 2t minus 1/4 natural log secant 2t plus c. All right. Is there any questions on that? Let you guys write that down.
I thought the integration of tangent was negative, and then I'm thinking something else.
Well, there's actually two different ways for the tangent. You could view it as, I could just write this off to the side, push this up a little. You could actually write tangent as sine 2t cosine 2t, and then have your u sub as cosine 2t du as negative sine 2t, but then have a half in there. Put over half, multiply by a half. 2. Okay. And then that would just turn into the natural log of cosine with the negative. So it'd be the same as the natural log of secant, but we already had that negative, so that's why it came to secant and the negative overall. That other negative would make this a plus. So that would be the same answer if we replace that, and then a 4th in front. If you wanted to exchange this part here, you could exchange that. This step here? Yeah. Well, if you look at this step here, we would get u as cosine 2t, and then du as negative sine 2t times 2, so we need the 1/2. It would come out front like that. And then we'd have 1 over u, so that's a natural log of u, cosine 2t. This would be a negative if it didn't already have a negative up front. Because this is a natural log, that negative distributes to the power of cosine 2t. So that negative 1 to the cosine 2t would make it 1 over cosine 2t. So you'd have natural log of secant 2t, because this would be just 1 over cosine 2t. 1 over cosine 2t is the same as secant 2t. Do you see that negative in the front? I could rewrite that a little. Basically, these two are the same. You could do either answer. Those are the same, because that negative in the natural log rule will turn into exponent. Does that make sense to everybody? Okay. All right, cool. What? Yes, I will post these. All right, so moving on from that one, we did get our answer there, and you could rewrite that, as we said, as the positive 1/4 natural log cosine 2t. Okay. Moving on. All right, does anybody know the integral of arctan? Is that the integral or the derivative? The derivative. So this comes to the case where we don't know what the integral actually is, just as natural log cases show. So we'd want to use parts. So what would we want to assign as our u? Could we split up an argument from the function? We wouldn't be able to take out, just as sine of like 3 theta, we wouldn't be able to take out the 3 theta. So we want to keep that whole, and because we can't integrate arctan, we're going to assign arctan automatically as u, because we can't integrate it. And then what would we assign the term that we have to integrate to get to v? 1. Nice. So we integrate both sides, and then we get v equals dt. X. Just t. Silly me. All right, and what did you say the derivative was?
1 over 1 plus x squared.
Okay, and what would our x squared be here?
4p.
All right, nice. All right, so plugging in t arctan 4t minus integral b du. Okay. dt there, dt. Okay, so let's see. It's all good. Okay, so what would we like to do next?
Oh, that's just a t. That's not dt for v.
No, that's just a t. Yeah, we're supposed to integrate down. So you integrate with respect to dt. That's where you're supposed to put that. Okay, so how do we want to integrate this term.
The same, right?
Maybe simplify a little. What were you saying?
Oh, 5 plus
2. U sub? Okay, perfect. Make U the bottom term, du the top term. And now what do we have to do to this function on the right to make it balanced? Because we don't have the 32. I could actually just solve it out for you.
You just put brackets. You can bring the 1 over 32 out from the integral, and you put brackets and redo the. Oh no. The TIL cancel, so you just have 1 over u.
All right, yeah, exactly. So we plug this in for t dt, and we'll get du over 32. So we can plug that in. And there's a 4 here, by the way. I don't want to get you guys confused, but u, when it was arctan 4t, you take the integral, it is 1 over 4t squared, but you have to take the derivative of the argument. So that 4t squared is, that 4t is there. So subbing in, we get 4, then we have the du over 32 u. All right, nice. T arctan 4t. Pulling this out, what would this give us?
The integration of 1 over u.
Okay, and what would that be?
ln.
All right, perfect. And what is u?
1 plus 16 t squared.
All right, nice. All right, and that would be your answer for this one. Did that make sense? All right, go ahead.
A few steps up, how do you do that with integral of 4t over 1 plus 4t?
Okay, so going back to our original parts, substitution. Oh, and if you guys can never see, just let me know. Going back up to here, we had to assign u as arctan 4t, and then make this 1. So our du, the integral of this is 1 over 1 plus x squared, but you have to take the derivative of the argument. So most case scenario, arctan of x is 1 over 1 plus x squared, but the derivative of x is just 1. So that's why it's usually not seen to have that derivative there. So we had to take the derivative and add it to the top for all of these. And it changed our answer just by a factor of 4. Is there any other questions? All right, cool. Go ahead. All right, actually in your textbook they do have the shortcut, and it's just a memorized formula that you could substitute in. So arctan would be 1 over a arctan x over a plus c. And then that would come out to 1 over a squared plus x squared, and then plus c. They have the formulas in the book. And arcsine, arctan is the one you would have to mainly know. Basically, you just memorize 1 over 1 plus x squared, and then the derivative of that, what's inside that arctan parentheses. All right, so we're good on that. Let's go to the next one. And I will be posting these online. I will write those formulas down for you too, so you could have those. All right, so another parts problem. We have two different types of functions. We're going to want to assign u and v. So which one would we want to assign as u? All right, perfect. Why?
Well, I mean, all this is thing called length. It's not something like the opposite where it's like you choose logarithms or the I is there's a like algebra, there's T for trigonometric functions, and because this is like algebra, I have to choose that.
Okay, that's a neat way of looking at it. But as Swanson said, our professor, for this section, if you can integrate both, you pick the u that makes it simpler. And that's an easy rule to remember. So x would definitely be simpler because it would come down to 1. All right, and then plugging in. Okay. Okay, solving that out. Okay, that was a simple one. Any questions on that one? Okay, so moving on to the next. Does everybody got this? Let me know. Anybody needs extra time? Well, you guys are copying up. I said a few surveys. Just bubble in 85. Just 85 to the top. Just bubble in 85. And 85 to the top. Just survey. Thank you. Do you guys get it?
That one.
Okay, perfect. Thank you. All right, does everybody have this copied? These will, again, be posted online. Okay, so starting on a new sheet. All right, we're going to do one last one of these. Just so you guys got this. All right, so what would you guys want to do here? It's no surprise it's parts. But why is that?
The layout rule, just like he said, also it's easier to derive.
Okay, so what do you want to assign as u?
X to the fourth.
X to the fourth. Now, if we assign u as x to the fourth, and dv as natural log x squared dx, what would we get for the integral of natural log x squared?
One half. No. You add divide, and then
All right. So in this situation, this is one of those cases where you look at your v's and you see if you can integrate both before you look at your u. Can we integrate the natural log of x? No, that's the perfect time. Once you see a natural log of x in an integral, then you're going to want to use parts right away. So instead of doing this, we're going to want to assign the natural log of x squared to u. Take the derivative of both. Including both sides. Ooh, this one comes out to be a little challenging here. Okay, so what are we going to want to do now that we have another natural log of x? For my UV? Oh, no, it's okay. Definitely verify. All right, but these terms would simplify down here and make it a fourth, but there's no difference. So now we came down to another natural log of x. So what does that mean?
Have to do it again.
Yes, perfect. So what do we want to assign as u? Okay, nice. Okay, so then we do it again. Still have this on the outside. And you don't want to drop that 2/5 off, so I like to do a big bracket so it distributes to all of them. Okay. Let me know if you ever don't understand anything, be it my handwriting. Perfect. Okay. And that 2/5 would distribute to this one as well. Did that all in one step, but put the 2/5 here. And it was a negative, so it makes it positive. Okay, double check that. Okay. Okay. So the only issue here is we had bounds, so we just have to leave that all down. But for time purposes, we will leave the bounds off, because I know you guys know how to plug in. Okay, did that make sense? All right, just do parts twice every time there's a natural log. Okay, so we're done with parts. Moving on. To trigonometric identities. All right, what's the main trigonometric identity that we need to know? This is key for your whole test. I think I heard it. Perfect. That's exactly it. And you don't even have to remember any of the others, because you can derive almost all of them out of this one. The main other one you would have to have would be either tangent or cotangent. You could just divide through by one of the trig functions and get it that way. So if you divide everything by cosine squared, both sides, we get tangent squared x plus 1 equals secant squared x. All right, and then if we divide by sine squared x, that's how you get the cotangent and the cosecant. Okay, so moving to the first problem. Cosine squared x tangent cubed x dx. All right, what would your first move to be in this problem? We have a cosine and a tangent. Usually it's a cosine and a cosine, sine, cosine, tangent, secant.
You can say tangent of a sine over cosine.
Okay, so you're wanting to transform tangent into sine and cosines?
Yeah.
That's a great move, because then you get just in cosines and sines. You want to be all in one type of area of identity. All right. Now that we're back in one form of identity, what would you like to do? Odd power of sine, odd power of cosine. What would you like to do? You want to do a substitution, right?
Yes.
All right, so what substitution would you want to make? Because we would have to have it squared to make that substitution. Okay, yeah. Perfect. So when you have an odd function that you have an extra of, you could pull it out. What would you like to transform that into? All right, perfect. Comes from the sine squared. Comes from the identity up there. And then that would just be over cosine x. All right. Then what do we do? After you're doing a substitution. All right, perfect. U sub. Setting u as cosine. U as negative sine x dx. Okay. Plugging in. 1 minus u squared over u du. Is there anything I'm forgetting? All right, perfect. All right, we can just split that up. And then we sub in. Yeah, you could. That's what we were talking about earlier. So that natural log rule still applies, and this is perfectly allowed. The negative sign comes from the du. So we needed the negative in the problem. And to make it easier, like, I used to not do it this way, but this makes it easier. If you just solve it for, like, as if this is a variable, you're going to sub back in, then you automatically have to put it in. So sine x dx, you just put sine x dx as negative du, du negative. And just, you don't even have to think about it. Because sometimes if you have like a derivative and it's like 2x and you have like an x on the inside, you're thinking, should I multiply by 2 or what? But then you just divide by 2 on each side and you get a 1/2. So all right, so how do I transform this part? Okay, I just split it up. So when there's only one term in the denominator, you can split up the numerator into 2 terms. So 1 over u minus u squared over u. And minus u squared over u becomes minus u.
Like on the table there.
Oh, it could be. It's off. I think it's actually this mic, and it's too close to my mic. This mic might be on. That makes sense. It's making noise when I move it. Okay. So moving on to another trig sub. What?
Might just be it running against the table.
Oh, maybe. I don't know. It's on my lanyard, so.
I mean the one on the table.
Yeah, here. Let me see if it's on. Doesn't seem like it's on. I don't even know. I think we just hope for the best for this one. Okay, so moving on. Okay.
Try cutting it off. If it's yours. See if it stops.
Yeah, I don't know if we can stop the stream. So I wouldn't want to shut it off. We might not even know what's actually affecting it, so I would have to like troubleshoot a lot. But focusing on this, what would you like to do? What would you guys like to do in this problem?
Either. Split up either or. Yeah.
Okay, so saying we split up either or. So if we go the tangent route and we wanted to make tangents at a fourth, so that can only become a secant squared to the square. And for us to assign secant as u, we'd have to have a secant theta tan theta. So we'd have, if we wanted secant, we would have to have an extra tangent, but we wouldn't have an extra tangent because all of the tangents would either have to be converted or you'd have another one left over. So if we stripped off one tangent, it would be tangent cubed, and then we could transform the tangent squared into 1 minus secant squared, but then you still have the tangent, so there would be too many tangents. So going to secant, you'd want to strip off secant in this situation. You kind of have to look at, if you assign u as this, you'd have to look at where your du would lie. So like here, if we assign tangent, we could have a secant squared, 2 extra secants left over that we could transform to tangent. As opposed to the tangent way, if we assigned secant as that, we'd have to have a secant tan and then 3 tangents that we couldn't transform to secant. So going the secant method, strip off 2 of those, have 2 of those, we'll have a tangent to the 4th, theta, d theta. Because if we make u tan theta, then du would be secant squared theta. And we already have 2 of those, so we can transform the others to tangent squared theta plus 1. Have that du, and then just have tangent in the 4th on the outside, du. So what would you like to do now?
Shouldn't that be squared? That tangent, the parentheses part, tangent squared plus 1.
Should it be squared?
Squared thetas.
Because why?
You have 2 secant squared thetas.
Okay, so That's a good point. It would be squared if we were converting both of those. That is a good point. But we're actually not converting both of them. We're making one of them this, and then the derivative of this is that. So this got absorbed in the du. The du is this entire secant squared d theta. Okay, yeah, making the actual substitution, you don't want both theta and u, two different variables in one integral. That's a great point. Okay, so putting both terms in, like it is supposed to be. Go like that, and then we're going to want to simplify. Imagine you guys got this. And we just integrate. All right, what else would be wrong with this problem? All right, perfect. I personally don't like changing them. It looks better to change them. If you don't want to change them, you could just add theta equals everywhere, and that's perfectly valid for the test. I don't change them because I go back to them later. So as in this step, if you change them, then you shouldn't waste time reverting back to tangent theta. So pi over 4. And then I imagine substitution, it will come out to 12 over 35. Okay, so moving on. Did that make sense? I could plug in the bounds if you want. But I imagine that wouldn't be too bad. Tangent pi over 4.
I think you just made a mistake on that second one. You put 1 over 7 tangent to the 7 plus 1
Oh,
over
it's 1 over 5? Yeah, autopilot. I wrote on the step above. Just substitution. Okay, so moving on. This one's a little simpler. Okay. All right, so what kind of substitution do you guys want to make here? Do you have something? Oh, okay. What on a trig sub? What do you want to do? Okay, so you want to set a u as, because we already have x, so you're saying a new u sub? Okay, so let's look at both of those. Integration by parts would be the method you would want to go with, but looking at yours, if we set u as secant theta, then our du would have to be secant theta tan theta. You only have one secant theta to work with. The other method you could do would be, you could multiply by secant theta over secant theta, and that would change it. So you could do that. But then again, you'd still have that x in the front. So you still have, you could do u as secant theta, and u in the denominator as secant theta, and then have your du, but then you still have that x. So regardless, you're going to have to do parts here. Okay, so what would you guys want to make u as in dv? All right, perfect. Nice. Having this as secant theta, well, secant x tan x dx, integrating both, is going to give us secant x. Multiplying them together. V du gives us this. All right, and what is the integral of secant x?
Oh, ln secant tangent.
All right, perfect. ln secant tangent. Here you go, Stephen. Thanks. If you could bubble 85 at the top, that'd be helpful. All right, ln secant tangent. All right, so is that our answer?
Yeah.
Okay. What? Yes. Clutch. That's good luck. Yeah, the actual integration of secant x would be the natural log of secant x plus tangent x. It's almost like the derivative, but there's a plus. Okay. So that would be it for trig and metric identities. Okay, does everybody got that one? Go ahead.
For the integral of secant x, we have to work that out on the test to prove how secant
No, you would not. But if you would, what would you have to do? All right, so the funny one would be you'd have to multiply by secant x plus tangent x over secant x plus tangent x. And that numerator would be the derivative of the denominator, which would just be secant x plus tangent x. And that's how we get natural log secant x plus tangent x. So you wouldn't actually if you memorized it, but you'd have to work it out if you didn't. I mean, in hindsight, you'd have to memorize secant x plus tangent x over secant x plus tangent x. So you might as well just memorize that instead. Okay, so everybody got this? Okay, cool. Moving on to some trig sub. All right, would you guys tell me what the x would equal in each of these?
In the second one, it's tangent.
All right, perfect. It would just be tangent. What happened? The third one? Okay. Okay, so is that all we would put for that?
You need an A.
You need an A at the front.
All right, perfect. So we need A's at the front of each of these. The way I like to remember all of these is there's a plus in this one. Secant comes before sign in the alphabet. So the variable comes before sign. The variable comes before because secant comes before sign in the alphabet. It's a little trick I use personally. It helped me a lot. Okay, so going on to the first example problem. Okay, so what would we have to do here? All right, some problems don't always are straight up as a trig sub. but a trig sub would definitely help with them. So how would we get that in the trig sub form?
Would it be by computer, how you would make it so that it's 4x plus 5 minus x squared, so that you could use 1/5 to, oh wait, no, is that what?
Okay, sound like some work happened. Go ahead, Stephen.
Then you take the square root of 5 by itself, and the square root of 5 plus.
Okay. Well, keep in mind that we do want it down to two terms like this. So,
Oh, so then you can factor it.
okay, how would we factor that? If you could fill out this survey and put 85s in those numbers, that'd be helpful. Thank you.
What?
All right, there's a special term that we could use in math that would break up something that is unfactorable into factors by either adding or subtracting those terms away.
Come on, quadratic. Not the b plus or minus the square root of b squared.
Oh, that's the quadratic equation. It goes along with factoring for sure. That's if you can't factor, then you would do that to get your roots. But in this situation, we would like to complete the square. So then completing the square, we would just subtract away the part that wouldn't end up in the square. So the 5 wouldn't end up in there. So we separate that. Show a little more steps than I did. Pulling out that minus, make that x squared minus 4x, leaving a space plus 5. Okay, so the 5 wouldn't go in the square part. That middle part is what we're trying to factor, and I pulled out the minus just from the x squared and the 4x. So how do we complete the square?
Sorry, dividing 4, making -2, so subtracting 2 on both sides.
Okay, so we would take half of this, and when you take half of that, that would actually become what's inside. So if we took half of that, that's going to become what's inside this, would be that term halved. But you would have to square it and add it here. Does that make sense for you guys? So you take half and then square it, that would be your third term. But if you take half of that, that would be what's inside the parentheses. So this would actually be 4 because we halved it and then we squared it. But because this is a -4, what do we have to put over here to balance it, the whole equation out? A +4. Okay, so we'd still have the negative here, and then we'd have the 9 there. Did that step make sense? There was a lot going on there. Okay, so moving on, we get the square root of 9 minus x minus 2 squared. You're going to want to rewrite it so it's positives, and then you can see where your x terms are. Okay, so what type of trig sub would this be? All right, thank you. Secant. So if we go to secant, we have x squared first, and then we have the a squared second. Is our x term first? They would have to be both positives. Like the x squared term, like in this case scenario, it's minus, but that's the second term. Like it's cumulative. Wow, you can switch these around, so it wouldn't matter, because this would be the same as this one. So it'd actually be sine. All right, perfect. So what would our substitution be?
Would be x minus 2. It would be 3 x minus 2.
Well, it wouldn't be that exactly. It would be very close. We're substituting this whole thing out, so the x minus 2 is irrelevant now. We could actually u sub it and just make this 9 minus u squared. So if you don't want to deal with the x minus 2, which I used to not want to deal with that, you could just do u is that, and then du would cancel out to 1. So you could do that substitution and then just do it later. But to skip that step, we could just make this x minus 2 3 sine theta. Because if this was u just there, it'd be u equals 3 sine theta. All right, so subbing in, get 9 minus 3 sine theta squared. And then now we still have to do our dx. And what would that equal? Just from this top term here. We could even add the 2 over. The 2 wouldn't matter.
I have a question.
Yes.
Would 9 be the a in this case?
Yes, 9, the constant is always the a. A represents a constant. Okay. Great question. Yes?
Why is it 3 sine?
Okay, so if we look at our beginning equations, the inside term is squared, and then when we write our x equals, it's a square root of it. So our inside term is squared, so when we bring it out, it's the square root of it.
Oh, okay, so the 2 has no relevance.
The x minus 2, it does because we're going to have to sub it in later. Like I said, you could do this u sub with x minus 2 and make it the square root of 9 minus u squared. And if it was the square root of 9 minus u squared, or 9 minus x squared, whatever substitution you want to make it look easy as possible for you, 9 minus x squared would be like this first one. So 9 minus x squared, x equals 3 sine x. And then you sub the u in after. But you could just do it right away like this, and then we just take a derivative, bringing the 2 over, make it 0. So yes, it would make it 3 cosine theta d theta. And we would write that right here. Okay, solving a little math out. Okay, and then we have to sub out. All right, so then what would we do here? We could pull out that 3. Oh, is it?
9. Yes.
Oh, yeah. Fix that. Oh, you know, my bad. This is 1 minus sine squared theta. It's a little small.
Yeah, cosine. It'd be like cosine times bar 3 cosine theta.
So you're saying this whole thing would equal cosine?
Oh, no, my bad. I thought you took out the 3.
I did take out the 3, so just this part.
Yeah, so you sub that 1 minus sine squared theta for cosine. And then you have the square root of cosine, which is just the brackets around cosine. to make
Okay,
sure-
so writing this out, you want to square root cosine theta, and we have the 3 cosine theta here. Usually the square root would always eliminate out. Okay, perfect. So yeah, pulling out the other 3, we have a 9, and then we have 2 cosines, cosine squared theta d theta. How do we take care of that cosine squared theta?
Half, no, you don't want to do a half angle.
Okay, I'm about to flip it, so will you guys be able to see that? We're at 9 integral cosine squared theta d theta. I'll let you guys get a minute to write it down so we can continue. So what were you saying to sub for cosine squared theta?
Half angle.
Yes, perfect. What would that be?
1 plus cosine 2 theta over 2.
Okay, nice. And we could pull that 1/2 out so we wouldn't have to work with it as much. Okay, does everybody got that? All right, great. Flipping this over. We're subbing out that cosine squared theta.
Might want to pull it down some.
Okay, thank you. I appreciate it. All right, so we're subbing out that cosine squared theta for 1 plus cosine 2 theta plus because it is a cosine. And we're going to take out that half. D theta. Integrating that. This gives us this. Gives us something like
2 sine.
this sine 2 theta, right? Should have worked out. Yes. Okay, now what do we have to do?
Oh, you have to do a triangle.
Yes, based off of this part here. So x minus 2 equals 3 sine theta. X minus 2 equals 3 sine theta. How do we work with that? I'm actually, we'll leave it like that actually. Actually makes it easy if you pull out the 9/2. Make it this. It makes it sine 2 theta. Do you guys know what sine 2 theta is? Okay, that would be a half angle, and it would actually be 1 minus cosine 2 theta over 2. Minus because it's not alike. If it was a cosine 2 theta, 1 plus cosine 2 theta over 2. If it's a sine theta, because it's not the same, it would be 1 minus cosine 2 theta over 2. Okay, but it's actually 2 sine theta cosine theta. So pulling out the 9/2, this is why we would make that substitution, because that sine 2 theta would turn into 2 sine theta cosine theta over 2. The 2's cancel. So it makes this problem a little nicer. But going back to your triangle, we'd want to make this x minus 2 over 3. We could just make it right away, arc sine.
Oh,
And-
wait, I have a question.
Yes.
Where did that cosine theta come from? After you integrate it, like cosine 2 theta, you get 2 sine theta 2 theta over 2.
Okay, like I was saying before, sine 2 theta. We can convert
Oh,
that
okay,
just
I
like
get
cosine
the
2 theta.
Formula.
Okay.
Split.
Okay. You got it?
Yeah.
All right, perfect. So now we have something a little easier to work with, 9/2. So we already have our theta. What's our theta?
Sine inverse of x minus 2 over 3.
All right, awesome. Okay, now all we need is sine theta and cosine theta. How are we going to get that? Oh, yeah. Okay, what goes on this side?
What is it? X minus 2.
Okay, nice. Sorry. And then that would be 3. And then we'd solve using Pythagorean theorem. And we get the square root 9 minus x minus 2 squared. Okay, so plugging it in, sine theta is the same as it was before. And then cosine theta is just adjacent over hypotenuse. So we get this. Should be. Okay. That is what you would have. And we just need the plus c at the end.
Would it be wrong just to leave it as 9 over 2 theta plus 9 sine 2 theta over 4? Alright.
By not expanding this out?
Yeah.
It wouldn't be wrong, but you definitely want to simplify. Lots of professors will take off for you not simplifying like a 4 over 2. Just as you were saying 9 over 6. And then the 2. So like, they would get bothered. So you definitely want to make as much simplification as possible. Okay, so moving on to another problem. Is everybody good on that one? Okay, cool. All right. Okay. So what type of substitution would we like to make here?
Secant.
Okay, secant. So we could assign x as what?
Is that a 9 or a 7?
It's a 7. Not bad.
The square root of 7. Secant.
Okay. Okay, so before you approach any integral, you want to look at the integral and find the easiest way to do it. Now, not saying that we couldn't do a trig sub here, but if we looked at it, what would you be able to do instead?
U sub.
Yeah, you'd be able to do a U sub. So always before on your exam, you're going to want to look to see what would be the easiest approach. If you can't think of something like that right off the bat, trig sub pretty much always works as long as the terms come out nice, like sines and cosines right them out. But yeah, we could just do a trig sub, U sub. We need that 2x, and we have an x, so we just have du. We need the 1/2, so just u to the 1/2. Okay, so then we just bring that up. It's 1/2 over 1/2, so it becomes 2. Yeah, it just becomes 2. U to the 1/2 plus c. Plugging in our u, just get that. Yeah, so you're going to always want to evaluate your integral. But yeah, you could have definitely done that method, but it would take a little longer. Moving on. What do you got on that one? All right, cool. Okay. Okay, so what would you guys like to do here? Okay, secant. I can imagine you could do some type of u sub with this, where you assign u, and then you solve du, and then you mix it around, so then u would become on a square root u in there, and then your linear function would be in the bottom, but it might not actually work out the best. So secant's the fastest thing that would come to my mind, as opposed to trying that. You always want to try things and work it out. You might not get it, you just erase it. Okay, so we get that. Substituting in, we get 9 secant squared theta minus 9 over 3 secant theta times 3 secant theta tan theta d theta. Okay. So what would we like to do here? This original problem had a 3 there, so that's why this became cubed on both. Okay, cool. You guys see that? I added a 3 to the denominator. That's why you can actually do the u sub, the easy u sub, real quick. It's because that 3 was there. Okay, so that would now make it, if we did this, 9 secant squared theta minus 1. And Steven, you said cancellation?
Can you cancel that? 3 secant theta.
Yeah, you would be able to. So 3 secant theta, with one of these 3's down here, I would make it 9 secant squared theta. Okay. So evaluating the top, what's secant squared theta minus 1?
Tangent.
Okay. So we'd have a tangent squared theta inside radical, so we just make it tangent theta, but we have another tangent theta there. So to make it tangent squared theta over secant squared theta. Taking into account that we also had a 9 on the inside would make it a 3. 3 over 9 is 1/3. Pulling that 1/3 out, we have this with the d theta. Okay, did everybody get all the steps? Okay. Okay, so yeah. Right here was a 3 to the third, secant to the third theta. And then that turned into 9 because one of the 3's canceled out with that 3 there. And then a secant canceled out, making it secant squared. So now we have secants and tangents. What would your approach be here? Because if we made u tangent, our du would be secant squared. And we don't have an additional tangent, not even enough tangents to do a u as secant. So what's another way to transform tangent and secant? I heard it over there. So we could transform this into sine and cosines. Okay, so this become 1 over that. Sine squared theta over cosine squared theta. Yeah, it's always a good route to go if you get a little stuck. So then our cosine squared thetas cancel out. All right, and how would we integrate that? Sine squared theta, how would we integrate that? Oh, my bad. Good stuff, though.
You do a half angle formula.
All right, nice. Which formula would that be?
1 minus cosine.
All right, I always like to pull out the 1/2 to begin with. Makes it a little easier. There was a half underneath, so that becomes 1/6. We can just integrate that straight away, making that theta minus sine 2 theta over 2 plus c. Okay. Transforming sine 2 theta, because that always helps out. What was sine 2 theta again? Sine squared theta would be 1 minus cosine 2 theta.
2 theta is, hold on.
Oh, 2 sine cosine.
2 sine.
All right, nice. All right, so we get 2 sine theta, cosine theta. It just makes the substitution even easier because you don't have to think about 2 of them, double for the triangle. 2's cancel out also, which is nice. All right, so how do we get these theta values?
The triangle.
All right, nice. What equation would we need to do the triangle?
The first one.
All right, nice, the substitution. So bringing that down, bringing it down here, we have x over 3 equals secant theta, secant inverse of x over 3 equals theta. Drawing our triangle, we'd have x here. Is that where x would go? We can also sub in our theta really quick. I like to do this first because we already got the theta. So we just only have like one little part left, it feels like. Minus, and then sine theta, cosine theta, we'll figure out. So how do we draw this triangle? If theta is here, theta is there, where does the x go? Does the x go here? Is it opposite hypotenuse for secant?
X should be the hypotenuse.
Okay. And then where would the 3 go?
On the
All right, perfect. Yeah, you could just think of cosine and then just flip it. So then we get 9 minus x squared, I believe. Or x squared minus 9. Okay, so that's what we'd have. Plugging in sine theta, what would we have? Sine theta would just be opposite, so square root x squared minus 9 over x. And then cosine theta is just 3 over x. So make it an x squared and make it 3 here. Okay, cool. And then that 1/6 would distribute. That is how we'd get that. All right, any questions on trig sub?
What's the power of that x on the bottom?
The power of the x on the bottom is a square. The cosine theta was 3 over x, and the x multiplied. Oh, yeah, that's fine.
Are you going to go over Taylor inequalities?
If we have time at the very end, I was actually thinking that could be an addition I could add would be Taylor series. But I am going to go through series. Actually, right after this one example of partial fractions. Okay. If there's additional time, I will tend to questions. Okay, cool. So we all got this? All right, nice. Doing our last type of integration technique. We're going to go to partial fractions. So there's two things we really need to know, two main tips. We're going to want to expand out to the highest term. So you expand out. All right, highest term. And irreducibles, we're going to want to make it like a linear function like ax plus b. Okay, so starting with our first problem, a little better. We're going to have dx over x squared plus 4 squared. So with these problems, you can almost tell right away. When you have something that you can factor in the denominator, then you're going to want to split it up and make it partial fractions. Okay, so how would we write this out? We're just going to expand this out, and that will be that. So how would you guys want to write this? Oh yeah, I'll take that. Thank you. Appreciate it. You too. Okay, yes, nice. Okay, so we'd have a over x. Now, it's only a power of 1, so we don't have to expand out. But say this was a power of 3. That's a power of 3. I just changed the problem. What would you write for our next term? Okay, and then the next? Okay, nice. What about the next term? How do you write that?
You do
Okay, so
dx plus e over x squared plus 4.
okay, so we have this so far. So what are you saying to do?
I just had a question.
Yes.
Do you want to go at decreasing, like for that x cubed?
Yes. So you want to expand out to the highest term, or go down in power until you reach a power of 1. So like, yeah, we have that x cubed. You want to go down x cubed, x squared, x.
Right.
Each with that, yeah.
For that last one, it's dx plus e.
Yes. And why would that be?
Because I don't know why.
Okay, so if we actually look at the second little tip I wrote, irreducibles, you want to make that linear term so we can account for all the polynomials and the degree of power degrees. So x squared plus 4, we'd have the dx plus e, but we'd also have to have another one because there's 2 of them. So fx plus g. X squared plus 4 squared, and what would this equal?
1.
It would technically equal, we don't care about the denominator. It would technically equal 1 over x cubed, x squared plus 4 squared. But then once you made a common denominator, it would all cancel. So that would cancel, but you have to make a common denominator. So the next step we would do would be a common denominator, because then you can combine terms. So yeah, you'd look what we need. you look, this already has the cube, so we just need the x squared plus 4 squared. So it'd be x squared plus 4 squared. And we need another x for that because we only have one. Just writing this out. We need another one of those. And then that last one, we just need an x. So it turned out to something like this. This is a cube. This actually changed a little. This is a cubed as well. And then this is b, so this is 1. Okay. We just need the c. Regardless of the c, we could put the c here. We want the c. Okay, so there we go. All right, I just wanted to write this out to show you one little tip that Dr. Swanson does. And in the past, when I've done partial fractions, I would try to expand out. And you want to do that when you can't plug in values. So you expand out, and you're trying to get the left to equal the right. So I would expand out, and you get all your x squared terms together in terms of a plus b times x squared or something. And you make a system of equations. But Dr. Swanson showed this cool tip where if you just let x equal 0, this term would cancel, this term would cancel, this term would cancel, this term would cancel. And all of this only equals the numerator. So you'd have that, and you'd only have like x squared plus 4 squared a equals 1. So that was something I liked because if you plug in 0 most of the time, a lot of things will cancel, and you only have one of the variables left. I doubt they're going to give you a giant one like this to solve for, but you should be prepped. Yes.
Wouldn't that x squared equal 0 as well for the a?
Yeah, it would equal 0, you're right, but it would just combine and be 16a equals 1, something like that. But yeah, but I was just showing it all canceled out. Okay. Okay, and then after that, we got a is 1/16, so that would just go up here into there. And then all we would have to do is, after we got a, b, c, all these terms, we'd integrate this as opposed to that. And that is what we do with partial fractions. Are there any questions with that? All right, so if the irreducible was cubed on the inside, let's see, if it was x cubed plus 4. All right, so if you could actually expand that out, and cubes always give you a root. So you would expand that out using that square, and after you did that, you'd probably find a factor. So then you'd have to remove that factor, and then you'd still have an irreducible. So you'd have that cubed function, and you'd have two separate ones. But say, for example, it was like this. Say, for example, it's like x cubed. Let me think of one really quick. X cubed plus x. Yeah. Just x cubed plus x, for example. We can make it squared. All right, so in this situation, that's a cube, and it's not irreducible because we can factor out an x. So if you factored out an x from both, it would be like factoring out a square. So you could do x cubed, and you'd factor out the square, and it would make it x squared plus 1 squared, like that. Do you see that? And then this would be an irreducible, but you got another term out. There's two terms, you'd add them together. Does that make sense? So you might have to factor further, but if you get an irreducible, you still have to put the dx plus e. Okay. We good? Okay, so moving on to series, and sequences in series. Okay, so what do we have to do when we have a sequence? Okay, great, keep going. So if we take the limit as n approaches to infinity and we get a number, it converges to that number. Perfect. To the number. And if we get like infinity or it's undefined, it diverges. Perfect. That's basically all you need to know for sequences. I'll show you an example that's a little weird from the average. This is just another identity that I'd like to tie in. So if we had sine 1 over n times n, how would you want to evaluate this limit? Take the derivative? Sounds like a good idea just because it's almost like in an indeterminate form. What you'd actually want to do would be try to get it into an indeterminate form so then you can take L'Hopital's rule. So if we try to put that in this form, we can actually rewrite it like this. So then we get sine of 0 over 0 is in an indeterminate form, but there's actually an identity that tells us that the limit, and you could take L'Hopital here, but then it'd make it more complicated. If we set x equal to 1 over n, we get sine of x over x. Has anybody seen this before? Do you know what that limit equals? This is just an identity. It's always one that's hard to remember, but it would be 1. And you could probably take L'Hopital, but this is an identity that you just have to know. I can't imagine anything further for sequences besides like squeeze theorem, but you should be good by just taking a limit, and it should always equal a number. Okay, so any questions on that? Sequences are pretty easy.
How is that just equal to 1?
What?
How is that just equal to 1? Like, can you prove it, or is it just,
It is one of those identities that you would know, but imagine if you did L'Hopital. The issue, you would just have to know that there is a proof behind it. Because if you took L'Hopital, you would get -1 to the n to the -2, and it would just keep increasing in powers, and it would just keep getting smaller and smaller as it approached 0. So that's why we have this identity that tells us it equals 1, because both of them would be going to 0, but like to infinity. So it just comes down to 1, and it's always 0 of 0, like even if you took L'Hopital like a million times. Okay, so let's go to actual series. Now, what happens in a sequence if it equals 0? What does that mean? Does it mean anything special? Does sequences go with the test for divergence?
somewhat, yeah.
Does it?
I mean, no, it doesn't. No, there's a different rule, but.
Okay. It actually wouldn't go with it because, as we showed there, that limit equaled 1. And technically, the test for divergence would tell us that that diverges because it doesn't equal 0. So sequences have nothing to do with the test for divergence. So if you get a number, that's the number it converges to. Okay, so going on to the next. Okay. So what do you guys want to do first with this function? All right, what's the first thing that we should always do with a limit? Plug in n. Okay, why would we want to take the limit?
Because that's how you get the answer.
If it converges.
Okay, so a limit as n approaches infinity would would go along with the test for divergence. So if we did that, you'd always want to test that first. you could do it in your mind or you could write it down. If you can't see it right away, I would write it down. But if it fails, it's pointless to have it there because if the test for divergence fails, then it tells you nothing. So solving it, okay, and what does this equal?
Go to negative, I have two, yeah.
Okay, so what does that tell us?
Nothing. No, it diverges.
Okay, why does it diverge?
That's the rule.
All right, so the test for divergence tells us that if you take the limit as n approaches infinity and doesn't equal 0, then it diverges right away. But if it equals 0, what does that tell us?
Now you have to use another test.
Yeah.
Use another test.
Yeah.
It tells us nothing. But use another test is a good one. Okay, so let's go on to the next one. Because that diverged. Okay, so what would you guys want to use here? There's always multiple tests we could use. I'm gonna actually use two different types of tests for this one. So what's one of the tests you could use here? All right, honestly, the comparison would be the best choice here because it would be the easiest and the quickest. Okay, so let's go with the comparison. What would you like to compare this to? Okay, perfect.
P series, that's convergent.
Okay, so as you were saying, 1 over n squared is a p series. So evaluating 1 over n squared is p is greater than 1, so it converges. But you have to make the connection between this series and that series. So if this converges, what would the sign have to be?
A would have to be less than B.
A would have to be less than B. So this would have to hold true because the big guy, if you have the big guy converges, then the little guy would converge. If the little guy diverges, then the big guy would diverge. So can we make this direct comparison?
I don't think so.
Okay, why do you not think so?
I don't know. I don't see it.
All right, so if you don't see it, that's fine. You can go right to the limit comparison test, especially if you can't make the direct comparison. Here, actually, it's a little tricky because this is actually not larger even as we go to infinity because it's coming from the positive side of 0. So if we plug in 1 here, this would already be 2 because e is 2.7 or whatever decimals. It would be still larger. And even if we go up to higher numbers, it would just get to 1.1 and stuff. So we can't make the direct comparison. So what test would we want to use? All right, perfect. So this is P series. If it's less than 1, it diverges. What happens if it's equal to 1?
It's inconclusive. No.
Is it inconclusive?
No. That's be greater than or equal to 1.
Positive real number. No, it does. That's not. Oh,
What happens if it's less than 1?
Oh, if it's equal to 1, it diverges.
Okay, what about?
Diverges as well.
Okay, what's that called when we have?
A harmonic series.
Yes. Does an alternating harmonic series diverge? If it was -1 to the over n.
Yeah. No.
It actually converges. We can prove that later when we're going to do an alternating series. There's two conditions we have to meet. Okay, so right now we're going to do comparison test using the limit comparison test. Limit. All right, so what does this tell us? We take the limit, clearly because it's called the limit comparison test. Does it matter if it's an over bn or bn over an? Okay, so let's lay out the rules for what we need. What would tell us if it converged?
If both series, if that limit as n goes to infinity of an over bn equals some positive real number.
All right, so some positive real number that's not 0. So it has to be greater than 0. Now, if it's an over bn or bn over an, and it's positive because of the absolute values, then it's going, and it's not infinity, then even if this was 2, this would be 1/2. So it wouldn't matter. It's just a ratio, so it would be just a constant. So I always do an over bn just because, but it wouldn't matter either way.
Why are you using absolute value?
They just have them in the formula.
Wouldn't that make it always?
It's always going to be positive, so you're really just looking out for any discontinuities or like infinity. You're really looking out for an infinity. If it equals infinity, it's not good. No. So, but it has to be greater than 0. So that's why they say not negative, but greater than 0. So if it equals 0, we have to use a different test. And there is another test for this one. So I'm going to move on to the next page. I can do it right here. So doing this limit, what would that give us?
It would get e to the 1 over n. That was what it was.
Yeah.
E to the-
He did AN. Did you do AN
I
over
did
BN?
an over bn, yeah.
All right, so starting from the beginning, an over bn, what would that equal?
E to the 1 over n squared times by n squared.
So the n squared.
Okay, so yeah, you could flip it up. I like to flip it up too. That would automatically flip up and it would cancel out like that. So this would be the natural log limit of the natural log of 1 over n. And what would that equal?
That would equal, if it goes to infinity, it would equal
1, perfect. So what would that tell us? Does this,
They have the same nature.
Yeah, they have the same.
okay, perfect. Exactly. An does what Bn does, and because An converges because An does what Bn does, and Bn converges because of p-series. So some iteration of that on your test would be perfect. You'd have to bring out the p-series, and then how you made this comparison, and it's greater than 0. So that overall converges. Okay, so let's move on to the next. Let's try this with the integral test, just so we can get some practice with the integral test. All right, so going back to the same series.
My tutor, I printed out.
All right, using the integral test. All right, what's the 3 conditions we have to prove? Okay, positive. All right, so how would we prove that this function is positive? How do you prove that's positive? Greater than 0, perfect. You want to write between those bounds or something. I like to write between the bounds 1 to infinity, like in this example, e to the 1 over n is greater than 0, so you show that's greater than 0, and then I heard continuous. Somebody else said that. You know, continuous and continuity always like threw me off, but really, you just narrow it down to 3 questions. Is there a negative square root? We don't even have, well, there's no negative square roots, because from 1 to infinity, no square roots of negatives. Will the denominator ever be 0 between 1 to infinity? No 0 in denominator. You just write 1 over, you could just write that. 1 over 0, and is there any natural logs? And then any natural logs less than 0. There's not even any natural logs, so no natural logs. Yeah, less than 0. Okay. And those, if those conditions don't happen, then it's continuous. Okay, so then what's the last condition we have to prove before we use this test? All right, perfect. Decreasing. How would you want to prove decreasing? All right, perfect. You take the first derivative less than 0. Or, in this case scenario, you'd probably want to be certain and do that. You take the derivative less than 0. But if it's a constant in the numerator, which the numerator is pretty much 1, because e to the 1 over n is not going to go like that much higher between 1 and 2. So it's pretty much a constant. And then it's an increasing denominator. That's the only time when you cannot take derivative, is when it's a constant in the numerator and an increasing denominator. But if you can't prove that exactly, do the derivative way. It always works. Way better. Okay, so now we can move on. So how do we take, what do we have to do? What's our bounds?
1 to infinity.
Okay, nice. And we have to change these to x's. I have to make it a function of x. It matters. You'll tell when you write the dx. Okay, I did. Okay, so what's wrong with this integral?
It's improper.
It's improper, so how do you fix that?
You gotta set up 2 integrals.
Two integrals, or do we need?
Not 2, just 1. You said t equals to infinity.
Yeah, we could use t or b. I like to use b, because that's how it's taught. But now we have this. How would you integrate that? U sub? What would be your U sub? Okay, so 1 over x, I'm going to write that as x to the negative 1, du as negative 1 over x squared. Does everybody see that? Okay, so if that's u, then we already have our du. It would just be negative. So we get the limit as b approaches infinity from 1 to b. I'm going to keep my x bounds as 1 to b. E to the u, du. And then integrating, we just get e to the u. E to the u was, we needed the negative from the du. It would just turn into 1 over x. With the negative, using the bounds, what is it? X equals 1 to b, limit as b goes to infinity. So we evaluate this. We just plug in. Get negative 1 over infinity plus e to the 1. And what does this equal? All right, so it equals minus 1 plus e. Okay, great. So what would that tell us if we get that answer for the integral? It what? Converges because it's a finite number. It's not infinity. Because e's a number, you add those as numbers. All right, so we got a finite number. Number finite, I guess. Converges. Okay. Moving on. Does everybody got this? All right, cool. All right, so let's do another here. Okay, so what do you guys want to do here?
You can do comparison test.
The comparison test? What do you want?
And
1.2.
1.2.
Yes.
because Arctan can't go past pi over 2. So we have pi over 2 over it and to the 1.2.
Okay, exactly. So we have pi over 2 over n to the 1.2. Now, can you make this direct comparison? It can't go past it. So that means that this will always be larger, right?
Yeah.
So in the comparison test, if the big guy converges, then the little guy we don't know about will also converge. writing that the other way. The parenthesis, the quotation just means that we know that we know this, like it diverges. So the big guy, we don't know, but because of this comparison, that implies diverges. Okay, so that's the rule for big guy, little guy. All right, so we made this comparison. So how would we prove that this converges?
P series.
Okay, so how would you do it with the pi over 2 in the numerator?
It wouldn't matter. It'd be like considered 1.
It wouldn't matter because we can factor it out.
Yeah.
You're allowed to factor out constants just like integrals. 1 over n to the 1.2. P is greater than 1, so series converges because of P test and P series test, and because it's greater than the original series, then that also would converge.
I have a quick question. Maybe you can do it.
Okay, I mean, you check it out.
It is this series of 1 over n times ln.
Okay, yeah. We could totally do this. All right. I'll do this one really quick because this one is a quick one. But we do have alternating and ratio to go. But we have a little extra time. So, okay, so we have this series. That one we figured out. Does everybody understand this one before we move on? It was a P series. We used comparison. It was greater than, so it also converged. Okay. Moving on to this audience question. Got this. 1 over n, natural log of n. All right, so what would you guys think right away on this question? All right, integral. Great, why? Perfect. You can see that right off the bat. So we do 1 to b, natural log of b to infinity. We do 1 over n, natural log x. We want to change to x. Okay, so then you assign u and x, so it would be like natural log x, and then you do b infinity, so it diverged. I'm pretty sure, right?
I got that from my next but I got the whole section.
You got a point for it diverge, so it diverges. So diverges. If you solve this out, it would just equal that minus natural log 1, 0, 0. This would even be undefined, so it definitely diverges. All right, so that made sense. Thanks for that question. Here you go. Okay. Did everybody get that one? That one made sense. The derivative was there. We used integral test. Okay. Moving on to alternating series. All right, when using an alternating series, what do we want to do first? What do we want to test for first? Yeah, for alternating series would be represented as this.
We want to see if it's alternating first.
All right, well, we would know right off the bat if it's alternating, if it's -1 in the end. So we know it's alternating. Okay, so the conditions for that test would be decreasing as 1. That's 1 for the actual test, decreasing. And that would just have to prove that the test for divergence fails. Or, yeah, fails. So we have an, and it has to equal 0. Okay, so decreasing would just mean an b plus 1 is less than an of b. So that's what we plug in. So basically, I never like to look at that because it's not as easy as taking a derivative less than 0. This just means the next term is less than the first term when you plug in n plus 1. Yeah, we didn't even need a b, just n plus 1. Let me rewrite this so it just makes a little more sense. All right, that has to hold true. Okay, but before we even do the alternating series test, because the alternating series test will prove conditionally convergent. So what we would want to do first is to prove absolute convergence, because if you prove absolute convergence, then you don't even have to do the alternating series test because it would obviously be conditionally convergent if it's absolutely convergent. So in this situation, you're given this problem, and you'd always want to start off right away with absolutely convergent. And if it fails, then you go to the next step and do alternating series to get conditional convergence. Okay, so what test would we like to use to prove this? Absolutely, if it's absolutely convergent or not. Not alternating series, but we're proving it with any other test.
Comparison.
All right, comparison. What would you like to compare it to?
N squared or basically 1 over n.
Okay. Yeah, I like to write it out like that first so we can make the direct comparison. And that also equals 1 over n. Which one's greater than?
1 plus 4.
You're saying this one's?
Sorry, the 1 over n is squared.
All right, perfect. So that means that
You have to use limit comparison.
we would have to use limit comparison because this one diverges, the big guy would tell us nothing. So limit comparison, we do limit of n approaches infinity over an over bn. Our an is n squared over n cubed plus 4 over 1 over n, right? And that gives us n cubed over n cubed plus 4. That equals 1, the limit. So what does that tell us if it equals 1?
Bn does, an also does.
And so what's that mean?
That means an is also.
All right, perfect, it diverges. Okay, so what will we do next? Finding out that it diverges absolutely. You'd want to do the alternating series test. So we take this, and what's one of the first things we have to do for the alternating series test?
You have to make sure.
All right, yeah, the limit equals 0. So, okay, so we can all agree that it does. We could factor out the n's, 1 over n cubed, and we'd figure out that it goes to 0.
I have to make sure that an plus 1 is greater than an.
This would go to 0.
Saying that the limit goes to 0, then an plus 1
Has to be greater than.
over an has to be greater than.
Not necessarily. You can have an increasing function that goes to 0. You could have n squared, 1 over n squared. Trying to think of one. But you could definitely have an increasing function that goes to 0. But you'd either want to do a derivative or just do the an plus 1. And I like to do the derivative. So I'll do the derivative really quick. Bottom times the derivative of the top minus top times the derivative of the bottom over bottom squared. Less than 0, it cancels out. We get 2n to the 4th plus 8n minus 3n to the 4th. Less than 0. So then we do a little math here. We get negative n to the 4th plus 8n less than 0. We could factor out an n and divide it out. So we get an 8 minus n cubed is less than 0. N cubed is greater than 8. So we could say for this series, everything above n is greater than or equal to 2, it would decrease. So we'd have to test the series in 2 and above. I actually didn't do this on my paper, so I had to do it there. So anything above 2 would show that it's decreasing. So we don't care about the first 100 numbers, as our professor has told us, because if it diverges, it diverges. If it converges, it converges, regardless of that finite amount of numbers. So greater than or equal to 2 proves it's decreasing. That means both tests were proven to be true. This going to 0, decreasing, that means we converge, but what type? What do you call this? Conditionally. Great. Nice. All right, is there any questions on that? All right, perfect. Good timing. Okay, so moving on. Okay, so what were we saying the first thing we have to do with the alternating series is? We can tell it's an AST because of the -1 at the end. What do we want to do first? Absolute convergence. Okay, what series, what's an easy one you can think of? What's the easiest test for you? Geometric's a pretty easy one. Not everything's raised to the n power, so it's a little, not so much geometric. But ratio. Ratio is a great one. I went in sequential order, as the textbook did. But yeah, the ratio. So what's the ratio test tell us?
That is one. Yeah. If the limit of an plus 1 over an is less than 0, then it converges absolutely. But if it's greater than 1, then it's divergent.
All right, so yeah, if it's less than 1, it converges. If it's greater than 1, it diverges. What happens if it equals 1?
It's inconclusive.
Okay, perfect. Different test. Inconclusive. Okay, so let's do the ratio test. So plugging this in, we don't have to include the -1 to the n because of the absolute value. So we get 1.1 to the n plus 1 over n plus 1 to the 4th. Flipping it, n to the 4th over 1 plus 1, 1.1 to the n. We do some cancellations. We get 1.1. We could factor it out because it's just a number. We don't even have to have the absolute values. Limit n approaches infinity. N to the 4th over n plus 1 to the 4th. Now, what's this limit equal?
Oh, I can't see it.
Oh, my bad. There you go. It equals 1. This is a 4, by the way. We don't have to do that expansion because we know the highest power possible is going to be a 4th. So we can write that's 1, but multiplying that 1.1 back in, we get 1.1. So what does that tell us for the ratio test?
That it is greater than 1, so it diverges.
It's greater than 1, so it diverges. Perfect. Okay, so what would we have to do now? Yeah, we would have to do the alternating series test to prove if it conditionally converges. So doing the alternating series test, we'd have to prove that the limit as n approaches infinity of an would go to 0. Looking at that,
It goes to 0. No.
yeah, that would be a more advanced limit that you'd have to take. Because when you do the derivative at the top, it would keep going n minus 1, n minus 2, n minus 3, forever and ever on. So this problem you most likely not get, but you'd have to prove limit as an goes to 0, and then, what's the other one? Decreasing. There's some type of rationale you could do with that because of the end of the 4th, but I wouldn't mind doing that, like, wouldn't want to do that in general. So let's do one last one, and we'll close out for today. Yeah. A Taylor series?
Yeah.
You'd like to do a Taylor series? Sorry. Yeah, do you have an example?
Yeah, the fx
All right, perfect. I was going to show a geometric. I'll just write it down really quick. I was just going to write this. But this one's pretty simple. You guys would be able to figure it out. I'll just write it down here. This would equal 27 to the n. That equals 4 over 27. I didn't write all the summations, but you guys would know. R is less than 1, so it converges. This is geometric, so if we wanted a summation, we just have to do the sum of it equals like 1 over 1 minus r. This is the Sn. We don't need that now. Okay, so that's how we prove. And this actually, the only two that work for telling us the sum of a series would be telescoping and geometric. And they might ask you that on the exam because they always want to know the number that it actually goes to. And telescoping, you use partial fractions like we did earlier. And geometric's what I just showed here, where it would be a ratio of terms. If it's less than 1, it converges, and then you use that formula, a over 1 minus r. All right, going to the Taylor series. This is the last thing we're going to wrap up for today. All right, so we're doing the Taylor series. Not Maclaurin because it's centered at pi over 4. Your function is just sine x, right? Is that the function? Sine x?
Yeah.
Okay. Okay, good, nice. So we make our table, right? Does anybody know the formula? What?
It's actually up to
Something like that? Okay, good. Nice. Okay, so that would be the formula for the Taylor series. We start at 0. Our function at 0 is sine x. 0 is, we plug in a is pi over 4, sine pi over 4 square root 2 over 2. I don't want to run out of time for this, but you had a question?
No, I was just talking about it.
Okay, so then we go to 2, negative sine x, negative cosine x, sine x. And then we get 3, we get 4, get negative pi over 2, that. Okay, so something like that. And you try to find your pattern when you go throughout it. So what you do is you just plug in all the things here. So square root 2 over 2, starting at 0. I don't want to be going too fast for you guys, but there. So we're starting at the first term. We want to start at 0. We don't start at the first term only if it doesn't go along with the function. Here it looks like it's fine, so 0 factorial. So x minus pi over 4 to the 0. And then you just keep continuing on with the next term. You plug in this term to that top part, and then your ends just follow suit. X minus a, your center. So then you keep doing that. So square root 2 over 2, and then it would be 1 factorial times x minus pi over 4 to the 1 plus square root 2 over 2 times 2 factorial x minus pi over 4 squared, and then you keep going on to that. And then we'd have to find our general form n, which would be something like square root 2 over 2 to the like n plus, what would it be, n plus, if it's 0, it would be 1, so it's positive. If it's 1, it's positive. If it's 2, it's negative. So it's probably plus 1. So 0 would make it positive. 1 would make it positive. 2 would make it negative. We wouldn't want it there. We'd want it like negative 1 to the n plus 1. And then 3 would make it, 2 would make it negative, 3 would make it positive. I mean, you'd have to really work around with this. There is a memorization for the sign, but you try to find your general form, and you correlate it with this term here. Sine, cosine, the negative stayed. So yeah. So then you get your general form n, you put it over n fourth. The hardest part would be the negatives. All right, so what's the hard, what was your issue with Taylor series? Did that make a little more sense, clarifying?
This one was like the one where it's like, it's alternating every other 2.
Yeah, that's the hardest part about the sine and the cosines, is when it alternates every other 2. There may be something in that math. It might be 2n plus 1, but, you know, looking at it, 2n plus 1 here would make it 6, 7. That would be negative. 2n, 4, 5 would make it negative. 1 would make it 2, 3 would be negative again. So you'd really have to play with it, you know? It's one of those things where, I don't know if that would help actually. 2, 4 positive, 2, 4. Yeah, that's the hardest part, would be that negative 1. I would look in your textbook because sine Sine has a specific function, like specific general term that you could just memorize, and then you wouldn't even have to think about it, because the negatives and positives is the hardest part with the -1 to the n plus 1, what I've seen and experienced. But that's a general way to do this. Is there any final questions? And if not, that would be the session for today. Thanks for coming, everybody. And if you could turn in your surveys to me, that would be very helpful. Thank you. Thanks, bro.